And I'm not like super concerned with the vocabulary per se, but it is important that you can look at these and tell the difference, because the approach that we take is very, very different for exponential equations than for other types of equations. So it's not the type of thing where, like with radical equations, I mean, it was really different than a polynomial equation, but you could just square both sides and then all of a sudden it was a polynomial equation, right? Exponential equations are a bit different. Like we can't just do like one thing to make it into something that we know how to solve. We have to sort of address it completely differently than other equations. So the first thing you should do when you see equations that have exponents in them is ask yourself if the exponents have variables or not. If there's variables in your exponent, then it's an exponential equation. We're going to use the methods that we're going to talk about today and on Monday to solve them. So we will define an exponential equation first. So exponential equations is an equation with variables in the exponent. There might just be one variable, there might just be one exponent, but some exponent has a variable in it. And the way we're going to approach these, there's two ways to approach these. The first we're going to talk about is called relating the bases, and when you can't relate the bases, we have another way of doing it. But today we're just going to talk about relating bases, and that relies on the idea that if you can make everything about both sides exactly the same except for one thing, you can conclude that that one thing has to be the same as well. So for instance, if I had like 3/4 equals x divided by 4, well, 3 is the only thing you can divide by 4 to get 3/4, right? And so x has to be 3. It's the only thing x could be. And we don't have to do any calculations to figure that out. It's just sort of a logical jump that if the fractions are exactly the same, except for the numerators, then the numerators must be the same too in order for them to have the same value. So we can do the same thing with exponents. If I have 5 squared equals 5 to the x power, well, there's only one thing I can raise 5 to in order to get 25, right? X has to be 2 because both sides have equal value, the bases are the same, and so the exponents have to be the same too. In order to get 5 squared, you have to raise 5 to the second power. And so x would have to be 2. And again, we didn't do like any operations to make that happen. It's not that we're like canceling anything or like anything like that or dividing. All we're just making a logical jump. We're just saying that if we make both sides look exactly the same except for the exponent, we can conclude that the exponents are the same also. And that gives us an equation without exponents or without variables in the exponent. So this is called the method of relating the bases. So solving by relating bases. So the first thing we want to do is rewrite each side of the equation so that they have the same base. So we want each side to be a single exponential expression. So that they have the same base. So there's sort of two pieces to this. One is that each side has to be a single exponential expression, which means you have one base, you have one exponent. So for example, like 5 to the 3x is a single exponential expression because we have a base, we have an exponent, we have nothing else going on. Whereas like 3 times 5 to the 3x is not a single exponential expression because we have an exponential expression in there, but there's also that multiplication, right? And that would get in the way. So that's not a single exponential expression. Or like, even like, I don't know why I'm obsessed with the number 5 today. Like even that is not a single exponential expression. We can write it as one by multiplying the exponents, but right now that's an exponential expression raised to another exponent. So our goal is to just have a base and an exponent, and that's the only thing on that side of the equation. And then the other piece of this is that those exponential expressions have to have the same base. So we want 5 to the something or 7 to the something on both sides. And then once we have that, then we can conclude that the exponents have to be equal. So we'll set the exponents equal to each other. Is each other one word or two? I always write it like with a small space, so like people could like think it was 1 or 2, like depending on, that way I don't have to actually know. I wasn't an English major. To each other and solve. So this is the approach we're going to take if we can. We'll talk again on Monday about like if we can't make the bases the same. But today we'll just do some where we can. So let's solve two to the 3x minus 7 equals 32. So when it comes to deciding what your base is going to be, I recommend choosing like prime numbers and just breaking everything down as much as possible. That way you can definitively tell if you can or cannot write it with the same base. Like for instance, if I had like 9 to the 3rd equals 27 to the x, well, I could be like, oh, I should write everything with a base of 9, but 27 can't be written with a base of 9. Whereas I see they're both multiples of 3, so if I try to write them both with a base of 3, if I can't do that, I know for sure that I can't solve by relating bases. But if I try using 9 and it doesn't work, it's possible that it could be broken down more. So always use a prime number as your base. I mean, unless they're already the same, in which case, whatever. But if you have to like choose what your base is going to be, always choose a prime number and break everything down as much as you can. And that way it's really clear if you can or cannot give them the same base or not. So here, the left side has a base of 2, and that can't be broken down anymore. And so the only chance I have of solving this by relating bases is if I can write the right side as 2 to some power. And so what I would do if I didn't know what 32 was as far as an exponential expression, I would just take out my calculator. So we don't expect you guys to know off the top of your head, you know, like how to write every number in the world as an exponential expression. But if you know what you want your base to be, just get out your calculator and just, you know, make a guess. Like, I think that 32 is 2 to the 7th power, and put 2 to the 7th power in your calculator. If it's bigger than 32, try 2 to the 6th, 2 to the 5th until you get what you're looking for. So it's okay if you don't know these, like just staring at them. Just use your calculator and guess and check a little bit until you get the right exponent. What is 32? Yeah, it's 2 to the 5th. Another thing is, even if you think you know it, like always just check it on your calculator just to make sure. It's really easy to, like, you know, off the top of your head be like, oh yeah, that's 2 to the 7th, and accidentally get it wrong. It's especially like the most common ones that are tricky are like things like 8. Like it'd be really nice if it was 4 squared, but it's not, you know, like it's sometimes tempting to think of that right away and write it down and then have it not actually be true. So just check them every time to make sure. So now I have a single exponential expression on the left, a single exponential expression on the right, and they have the same base, which means I can conclude that their exponents must be the same as well, because that's the only way for those two expressions to have the same value, right? 2 raised to some power is only equal to 2 raised to the same power. And so that means that 3x minus 7, which is the exponent on the left, has to be equal to 5, which is the exponent on the right. And then that just gives us a linear equation we can solve. So add 7 to both sides. And we get x equals 4. It really seems like late in the year for there to be flies. Right? Like, shouldn't they have all frozen by now? It's a hardy fly. Or maybe it's like genetically modified. It escaped from a lab. Somebody told me there's like a animal like testing thing like under the animal science. I mean, I've never been over there, but I've heard there's like monkeys and stuff. Is this true? Have you guys like heard of this? Who knows what's going on?
Animal bioscience building, they have like an entire gate blocked off from the basement.
Yes, that's
so you can't go down into the basement.
It's where they genetically modify these flies to live in the cold winter of Montana. Okay, that makes sense? Okay, let's do some more. How about 8 to the x equals 64 divided by 4 to the 2x. Okay, so there are a couple places in these problems where it's kind of common to get a little bit stuck. One of them is when you're dealing with fractions, because if you have like 1 over 3 to the x equals 3 to the 5th, like you don't have common bases. I mean, well, you kind of have common bases, but the left side of the equation is not written as a single exponential expression. It's 1 divided by an exponential expression, right? So just like if we had like 5 times 3 to the x, that's not just 3 raised to some power. Well, 1 divided by 3x is also not, or 3 to the x is also not a single exponential expression. It's got another operation going on. So we have to have ways of bringing things up out of the denominator. And the way that we do that, so to get expressions, so exponential expressions, the denominator we're going to change the sign on the exponent. So back in like R.7, when we worked with our exponent rules, every time we simplified, we wanted our final answers to not have negative exponents. And so we used the rule that if you have like x to the negative 5th, that's the same as like 1 divided by x to the 5th. We're using that same rule here, we're just using it backwards. So now it's not that we don't want negative exponents, it's that we don't want denominators. And so if you have like 2 divided by x to the 3rd, we would rewrite that as 2 times x to the negative 3rd, and that gets that out of the denominator. So almost everything we do with respect to relating the bases, like the actual process of solving the equation isn't too challenging once we get what we want on both sides. So the challenge is rewriting both sides of the equation, and you'll use your exponent rules a ton for that. So if you, like as we're going through examples today, if you're not sure, like if you look at it, you're not sure what exponent rule would help you to rewrite it in the way that we rewrote it, look for that half sheet of paper I gave you when we did R.7 that has like the list of exponent rules on it, and just like keep that with you when you do your homework, because you can find an exponent rule that'll help you do anything you need to do. But sometimes it's hard to just like have those pop into your head exactly as you need them. And if you can't find it, just let me know. I can print you another one off. But those exponent rules from R.7 are going to be like the key to all of this. That's exactly what we need to rewrite all of these. So back to our problem here. If I want to get that 4 to the 2x out of the denominator, I'm going to just change the sign of the exponent, so it's going to be a negative 2x. So this gives me 8 to the x equals 64 times 4 to the negative 2x. And now that I don't have any fractions, I'm going to deal with the numbers 8, 64, and 4, because none of them have the same base, right? So I see that they're all multiples of 2, so they're all divisible by 2 because they're all even. And so I'm going to try to rewrite them with a base of 2. So 8 is 2 to the 3rd. And 64 is 2 to the 6th. I don't need parentheses on that one. And then 4 is 2 squared. And notice that when we do this, like, it's a little different from when we normally solve equations, because normally when we solve equations, we like do things to both sides, like we do operations on both sides of the equation. Here, all we're doing is rewriting. Like I'm not performing an operation to change 8 to the x to 2 to the 3rd to the x. I'm just saying 8 is the same as 2 to the 3rd, right? So I'm replacing the number 8 with an expression that's equivalent to it. So I don't have to do anything on the other side to counterbalance that, because I haven't changed the value of anything here. I just made it look different. Does that make sense? So now we'll simplify even further. I don't want those parentheses on either the left or the right, so I'm going to use my power rule and multiply my exponents. So we get 2 to the 3x equals 2 to the 6th times 2 to the negative 4x. And now we're almost there, but on the right side we have a product of 2 exponential expressions rather than a single exponential expression. And so I want to add the exponents, right? If you multiply 2 exponential expressions with the same base, you can add the exponents. So we have 2 to the 3x equals 2 to the 6 minus 4x. So we added those, but I added a negative, so it becomes subtraction. Now I have a single exponential expression on each side. They have the same base, so I can say that the exponents have to be equal. So 3x equals 6 minus 4x. And we'll add 4x to both sides and divide both sides by 7. So x equals 6/7. Is it possible to get an extraneous solution when we solve these equations? Why not? Sorry?
You can't get a 0 when you're multiplying exponents.
So what would be wrong with getting a 0?
It'd be undefined if there's a 0 at the bottom, but you can't.
Right, so if we had a fraction that had a denominator of 0, yeah, that's exactly right. That would be undefined. How come that will never happen with exponential expressions?
An exponent of 0 is 1.
That's true. An exponent of 0 is 1. What types of equations?
By itself,
Uh-huh.
it's bigger.
That's true. Or smaller if you divide, right? What types of equations have extraneous solutions? So rational equations, right, we had restricted values. So numbers that couldn't be in the denominator. When we had radical equations, we had to check our solutions. And then when we just did logarithmic equations, we had to check. What makes those operations different than other operations? Division, square roots, logarithms are different from other operations because okay, I'll let you think about it for a little bit. Because they have domain restrictions. So square roots and division and logarithms are the only operations that are not defined for all real numbers, right? We can't divide by 0. We can't take the square root of a negative. We can't take the log of a non-positive number. And so it just coincidentally turns out that the operations that are not defined for all real numbers cause extraneous solutions. It's not a coincidence at all. It's when you solve, you could end up with something that's not in the domain of the logarithm, the fraction, or the radical, right? Because those are the only operations that have numbers that aren't in their domain. Everything else is defined for all real numbers. So no matter what you get, it's going to work, right? So in particular, exponential functions are defined for all real numbers, right? You can raise a number to any power, negative, 0, positive. And so no matter what we get, it's going to work because our exponent can be anything. So the only equations that result in extraneous solutions, where you have to check your solutions, are equations that involve division, i.e. fractions, radicals with an even index, in particular square roots are the ones we use most often, and logarithms. So if your equation doesn't involve any of those, then you don't have to worry about checking for extraneous solutions. In this case, we do have a fraction, but like Shalea said, the denominator can never be 0 because it's an exponential expression with a non-zero base, right? So we don't have to worry about that. We're never going to give you one that's like 0 to the x because that would just throw the whole thing out, basically. It would have no solution. So here's one for you guys to try. Oh, this is a good one. The square root of 7 divided by 7 equals 7 times 49 to the x plus 3. Oh, that is a good one. So fun. These are kind of like puzzles, right? That's fun. Who doesn't?
Square root of 7 times 7 equals 7 times 49.
Okay, so what do we have to do? So if this is like an exponent of 1 down there, you're right, we can bring that up. What do I have to do to the exponent?
Make it negative.
Yeah. So this will be the square root of 7 times 7 to the negative 1 equals 7 times 49 to the x plus 3. Very good. And then, Ellen, what do you want to do next?
Can you divide by 7?
You could divide by 7. If we divided by 7, though, like this wouldn't cancel because it's 7 to the negative 1, not 7 to the positive 1. And so if we divided by 7, we would just end up with a fraction on the left again, which we just got rid of, right? What about 49? Can I rewrite that?
You can bring the exponents to the square.
What now?
7 squared.
Yeah, so we don't want to do like the key to all of this is that you don't actually want to do any operations with anything. Like you don't want to like move anything over or anything like add or subtract or multiply or divide. We just want to take the numbers we have and make them look different. So that 49, I'm not going to do anything with the exponent, but that 49 is the same as 7 squared. So I don't have to add or subtract or multiply or divide on both sides. I just want to take each number individually and make it look different. Does that make sense? Okay. So this square root of 7 times 7 to the negative 1 equals 7 times 7 squared to the x plus 3. Ryan, what do you want to do next?
Can you make the square root of 7 to the 1/2?
Yep, absolutely. And that's the other place where it's easy to get a little bit stuck, is with radicals, because they don't look like exponents. So in my little list up here in orange, so to rewrite radicals, remember that the nth root of x is equal to x raised to the 1 over n. And in particular, the square root of x is equal to x to the 1/2. So that one is kind of easy to forget because we don't see like the 2 in the square root, right? Square root has an index of 2, but we don't like write the 2 right here. So it's not as easy to just see what the denominator of that fraction should be. So these two things in orange, like if I were you, I would maybe like circle them or, I don't know, highlight them in some way. Because often when people get stuck on these problems, it's one of those two things. So if you get stuck, go back to those two things and check if one of them will help you. Because often it will. Lane, what should I do next?
Multiply your x plus 3 times 2.
Uh-huh. Yeah, to get rid of those parentheses, I can multiply my exponents. So, and like all this stuff that I'm doing, there's not really any order to it. Like, you know, like the order that I decided to rewrite the 7 as 7 to the negative 1 and rewrite the square root of 7 as 7 to the 1/2. It's not like if you did that in a different order, it doesn't matter. We're just kind of like looking at each one of these factors individually, getting it to look the way we want so we can put them all together. So I have 7 times 7 to the 2 times x plus 3. Notice that we need to put the x plus 3 in parentheses because we're multiplying the two exponents. So the exponent of 2 by the entire exponent of x plus 3. We don't want to just multiply it by x and then add 3 because that would mean something different. Peyton, what do you want to do next?
I added the 1/2 and the negative 1 exponents together and then multiplied the 2 times.
Yeah. So when we're multiplying exponential expressions, we can add the exponents. So this one becomes 7 to the negative 1/2. It's negative 1/2 because 1/2 minus 1 is negative 1/2, not because 1/2 times negative 1 is negative 1/2. I added them, I didn't multiply them. Even though in this case you get the same thing. And then over here, we can distribute that too. So 2x plus 6. Shalea, what do you want to do next? Yeah, we want to combine the two expressions on the right into a single one, right? The operation between them is multiplication. And remember, this is a 1. So what do we do with the exponents when we multiply? We add the exponents. So we have 7 to the negative 1/2 equals 7 to the 1 plus 2x plus 6. And now we have a single exponential expression on both sides. They both have the same base. And so I can say that negative 1/2 has to be equal to 1 plus 2x plus 6. Yes?
When you rewrite it, could
Uh-huh.
you just add 1 to the 6 and make it 7?
You could. I try not to like do too much at once on these just because it can be really easy to accidentally like do something that's not true. But yes, that's the same as 2x plus 7. So I have negative 1/2 equals 2x plus 7. And, oh, I don't know. I guess I'll just clear fractions. So negative 1 equals 4x plus 14. And so if I subtract 14 from both sides, I get negative 15. And then divide both sides by 4, and I get negative 15 fourths equals x.
Could you do this as a decimal, as a percentage?
It's the same thing. However, we prefer fractional answers because if you ever want to do something with it, there's no guarantee that that decimal is going to be terminating, right? A lot of you that give me decimal answers, whether they're exact or not, right? Like if that was negative 11 thirds, you can't write it as a decimal because it's not exact. So I'm fine if you give me exact decimal answers, but you need to be able to distinguish between when they're exact and when they're not, right? So this one is exact because when you divide by 4, you get like a 0.25 or a 0.75 or something like that. But if the denominator was like 7, then you'd have to round to give a decimal, and that's not an exact solution. So that's why I always go with fractions, because then I don't have to decide if it's okay to use a decimal or not. Let's do one more. Oh, let's do this one. So one of the nice things about relating bases is that you actually don't even need to know what the base is in order to solve the equation. So for instance, if I have b to the x squared over b to the 10th equals b to the x to the 3rd power. Well, it doesn't really matter what b is as long as I can write both sides as a single exponential expression with b as the base. And I mean, these are actually even kind of nicer because you don't have to figure out like what power of 782 is, right? Like the base is just b. So all we have to do is use our exponent rules. So on the left side, I have b to the 10th in the denominator. So I'm going to bring it up and call this b to the x squared times b to the negative 10th. And over here, I'm going to multiply my exponents. And then on the left side, I can add my exponents because I'm multiplying. So b to the x squared minus 10 equals b to the 3x. And now, because we're just setting the exponents equal to each other, it doesn't matter what b is at all. It just drops off. So we get x squared minus 10 equals 3x. What should I do from here?
7 equals 0.
Yeah, I need a 0 on one side because I have two terms containing my variable, and they're not like terms. So I'm going to get everything on one side and then factor. So I have x minus 5 times x plus 2 equals 0. So x equals 5 or negative 2. And again, extraneous solutions aren't possible, so both of those work.